Okay, this video will be about potential energy, specifically gravitational potential energy. Um, you can find the notes or a version of these notes on Friday, April 3rd. You can see I crossed off elastic spring potential energy for this shutdown. I have to trim some things out, so I'm going to trim out the spring potential energy. You can read the notes online from them if you want. You can try some of the problems if you want. Uh, it wouldn't be a bad idea to just at least have a general idea of how elastic potential energy works. So for this, specifically from the workbook, pages 59 to 64, so that should be the end of the Unit 3 workbook. Questions 13 to 31 should be specific to gravitational potential energy. Question 37 involves just gravitational potential energy, but all the other questions for those last 5 pages will involve spring potential energy as well. Elastic potential energy, in other words. So you can give them a try if you want. We're just not going to focus on them. There is a pretty decent textbook link from Pearson. It should be linked right to your gravitational potential energy section, so it wouldn't be a bad idea to give it a read. But yeah, this can all be found on April 3rd. So there is lots of different types of potential energy. So potential energy literally is just the energy stored in an object that's just ready to be converted into kinetic energy, if you will. So it's just ready to be turned into motion. So there's chemical potential energy, electric potential energy, elastic potential energy, gravitational potential energy, there's nuclear potential energy, there's lots of different types of potential energy. So that's just all based on different properties of materials or certain things, if you will. We'll get into electric potential energy in our next unit, but chemistry classes should probably talk about this in some regard for you guys. But yeah, for grade 12, we are just going to cut out elastic potential energy. So you can see here, gravitational potential energy is just the work done by or against gravity. So well, what does that mean? Think about trying to lift something up in the air. So here I have a little tiny box that I just kind of drew in real quick. And if we want to lift it up in the air, we're going to have to introduce energy into this system. So the very minimum amount of effort, force that we're going to have to put in just to make this thing go up is we're going to have to match its weight. So, so if we know what the actual weight is, remember that's just your mass multiplied by your gravitational field or your acceleration of gravity. And we're assuming we're on Earth, so that means we have acceleration of gravity or gravitational field, whichever you want to call it, pulling down back towards Earth. So if I raise this box from the ground to some unknown distance, we'll just call it final height, if you will, or final distance, we're going to actually do some work. We're going to do apply a force over a given displacement. So the minimum amount of force that we're going to have to put in here is going to be equal to the weight, and it will go up. It'll go up slowly if we just make it equal to the weight, but if we make it just slightly larger, it'll start to go up just a little bit quicker. But when physicists do this, they just look at the bare minimum and say, okay, fine, we're just going to apply the weight. So we have the weight applied just to make it go up, just to overcome the weight that's going down, and that will be the work done to elevate any mass up a certain height. So of course, work done is your change in energy. So if we manipulate this just a little bit further, so the minimum amount of applied force that we have to put in here just to go upwards is going to have to be the mass times your acceleration of gravity, and then multiplied by your overall change in displacement. If you consider that your initial displacement or initial position, if you will, was 0, we're on the ground, we could just say then that it should be your mass times your acceleration of gravity times your final height. And that should tell you what your work done is. And so because we're talking about vertical distance only, we can get rid of the D, the position, and just call it H for height. So that way there's no miscommunication, because this delta D can be interpreted as vertical, horizontal, or even at 10-degree angle, if you will. But if you leave it as height, then it's only interpreted as a vertical change in position. So that is your basic equation for your gravitational potential energy. It is just the work done to move something in a gravity field, or move something against the acceleration of gravity to elevate something. Or if you remove that applied force from this box, if you can imagine holding this box, If you let go of it, it's going to fall straight to the ground. At that point, it's the acceleration of gravity that's doing all the work, and it's going to be the exact same amount of work just to go back downwards. So you can have positive work. In order to elevate a box, you have to put energy into it, and you can have negative work. If you remove this, you're going to lose that energy, so work is therefore considered negative. Now the symbol for your potential energy, the generic symbol is just EP, energy potential. I've also seen it written as capital P, capital E for potential energy. But specifically for gravitational potential energy, it's just the big capital letter U. For reasons unbeknownst to me, I think I knew at one point, but not anymore. So it doesn't really matter. I've seen it written in many different ways. I'm still used to using the big capital letter U, at least in my equations, but in the end, doesn't really matter what you call it. But that is the symbol I'm going to use for gravitational potential energy. So gravitational potential energy only relies on the vertical height. We don't care about the hypotenuse, the displacement along that inclined plane. In fact, it's going to make some of your inclined plane problems a lot easier, because before we would be concerned with the parallel acting force of gravity going down the inclined plane, so the parallel component of its weight, if you will. So we don't have to worry about that anymore if we're going to involve your gravitational potential energy. We just need to know what the overall elevation difference is when this thing is actually in motion. So I'll just kind of prove it to you with this next little example. So suppose it's a 10 kilogram cart. Let's just make up some numbers here. We'll say we have a height of 3 meters. We have a hypotenuse, so the distance down the inclined plane is 5 meters. And if you recognize it, that makes this a 3, 4, 5 triangle. So you'd have 4 meters along the x-axis, but we don't care about that. It's just sort of an extra little piece of information. So that should tell you at the very least, if you got a 3, 4, 5 triangle, that this is almost a 37-degree angle, if these are the numbers I'm going to use. So at least that's how you know where that number came from. That's why it's specific to 36.88. So it's about a 37-degree angle. So if we compare the work done by the cart's weight to the potential energy of the system. So let's first do the work done the way we did it, or at least use the forces the way we did it last unit. So work done would be the parallel acting force to the multiplied by the displacement. So we have to use a parallel acting force. So that would just be the parallel component of the weight. So in order to figure that out, we have to have the free body diagram. Since it's a frictionless surface, there should be nothing going to the right, which would be up and to the right. So all we have to worry about is the parallel component of its weight. And that has its own specific equations. So I'll just change that in my work equation. So now we have the only force that's involved in the direction of motion is going to be our parallel component of the weight multiplied by the hypotenuse, the inclined plane. So if we actually work that through, if you remember, the equation for your parallel component of the weight should be mg sine theta. So if I just put in the numbers that we have here, we've got 10 kilograms multiplied by 9.81 meters per second square, multiplied by sine of the angle of incline, and then multiplied by the r change in displacement down the inclined plane. So this is a parallel force to the displacement. Remember, when you do your work equations, you always need to use a parallel acting force to the displacement. When they're not parallel, that's typically when you're going to add in the multiply by cos theta, but by using this predetermined equation for your parallel component of the weight, we don't need to bother with multiply by cos theta because this makes it parallel already. So work that through, you end up about 300 joules for work done. So 294 joules if I only use 3 significant figures. And then if I compare that now to only my gravitational potential energy. So my gravitational potential energy is a nice quick little equation, just mgh. So knowing what I know the mass, I know the weight, I know the acceleration of gravity, 9.81 meters per second. So if I multiply it by 3, I'll get the exact same result, right down to a T. So if you're going to involve gravitational potential energy, you can more or less, especially if something's on an incline, you can ignore the component, the work done by the weight, whether it's the parallel component or the perpendicular component. We can just ignore that altogether because we're going to involve this for now on, your gravitational potential energy. It's the same result, so we don't have to worry too much about free body diagrams. Working with energy is quite a bit easier in my opinion because you don't have to show your work with free body diagrams. You can just try to follow what the energy is doing. So hopefully that makes your life a little bit easier. So try to always remember, if there's an elevation change, if something goes up or goes down, it's going to change its gravitational potential energy. Regardless of what else is going on, if there's any change in your vertical elevation, your gravitational potential energy has changed. So think of a pendulum. You guys probably saw a little bit of pendulums last year in your physical science 20. So your pendulum just swings back and forth. In a perfect world, there'd be absolutely zero energy loss. So it would just do this back and forth forever and ever and ever. But we know that there's technically air drag. There's going to be a little bit of friction on the rope. So it would technically slow down. But if we think about just fundamental physics, this should just go on forever if we can somehow ignore gravity and air, not gravity, friction and air drag. So I bring up the pendulum for this reason. You can see that when the pendulum swings, it has a change in elevation, right? It has its highest point there, goes down to its lowest point, then back to another high point. So we're constantly going from a point where you have maximum gravitational potential energy to maximum kinetic energy, because it stops briefly at both ends and it goes its fastest speed right down at the middle. So it's constantly changing its energy from gravitational potential energy to kinetic energy to gravitational potential energy to kinetic energy to gravitational potential energy, and back and forth and back and forth and back and forth. At its highest points where it stops, that's where it's at its maximum height. It stops completely, so all you have is a gravitational potential energy. At its lowest point here, right at the center of its swing, it's at its lowest point, we can actually set your height to zero, because when it comes to gravitational potential energy, you can more or less set any point at zero. I typically will make that the lowest point just to keep life simple, because we are just talking about the amount of energy exchange when our elevation changes. So really you can set ground at zero anywhere you want. You can be 10 feet in the air and call that zero, just to keep your life simple. So at that point, I just need to point out that when it comes to a system like this, if we're ignoring all friction and energy loss, we can say that your initial gravitational potential energy, when it's at the highest point of the swing, must be equal to its kinetic energy, so its final kinetic energy when it's at the lowest point of the swing. Or likewise, if we're starting at the lowest point and it's going up to its highest point, we can go backwards and say, well, technically that would be the initial kinetic energy must therefore be equal to your final gravitational potential energy, because energy cannot be created or destroyed. So whatever energy we have in the system must still be in the system. It can just change from one form of energy to another. So that's a lot how pendulums are looked at. And again, once you introduce real world physics, there will be a little bit of energy loss. But if we're talking about just going for one swing motion, the energy loss isn't significant enough for it to really matter. So you can more or less ignore that as far as fundamental physics are concerned. I have one final question just to kind of walk through with you. It seems like a bit of a morbid question, but it's an interesting one. Suppose we have, this is on question number 21, I think on page 59, maybe page 60. Can't quite remember what page it's on. So you have a bird flying at 4 meters per second in the air, and it suddenly dies of a heart attack, as it happens once in a while. When the bird strikes the ground, it's traveling at 11.7 meters per second. So if we ignore all air resistance, let's determine how high above the ground the bird was when it passed on. So got a little GIF animation from a little website there, which I probably should have put on there. Oh well. It's flying through the air, 4 meters per second. It's at some initial height. We don't know what the initial height is, but it was at some initial height. All we know right now is 4 meters per second, so we know it has kinetic energy. So that's the initial. Poor birdie suffered mortality, died, fell over the ground, died while in motion. It happens. Fell over the ground, hits the ground, now it's on the ground. We know that afterwards it has no gravitational potential energy because it's on the ground. If your height is zero, you have no gravitational potential energy. But it does hit the ground, it's going to have a speed. This is a projectile motion problem technically, but we're not going to treat it like a projectile motion problem. We're just going to look at the energy, and you'll get the same result. If you felt like going back to unit 1 and figuring this out using projectile motion, you might guess it would work out just the same. So let's point out what energies are involved. Initially, We're at some height, so we have to have gravitational potential energy. Also, initially, we have a speed, so we have to have kinetic energy. In the end, we're on the ground, so we don't have gravitational potential energy, but we do have a speed. When it touches the ground, it's going to that 11.7 meters per second, which means we have kinetic energy in the end. So we have to follow the energy in this question. So that means my initial energy must be equal to my final energy, because we are ignoring all energy lost due to air drag. I'll talk about that kind of stuff in the next video. So if we consider what we had initially, we had speed and we have a height. So therefore we have two types of energy to start with. We have kinetic energy, we have gravitational potential energy. So we have to be able to create our own equations based on what is actually happening in the system. So consider they all have their own equations. So I end up with 1/2 mass velocity initial squared plus mass times your gravitational field multiplied by your initial height should be equal to 1/2 the mass times your final velocity squared. And that's your setup for this particular equation. Now this question doesn't give you the mass of the bird, but that's fine because mass is in every single one of these terms. So that's also why I'm not going to solve for the kinetic energy individually before and kinetic energy afterwards. I don't know enough information. But luckily, the masses are in every single part of this equation, so we can just cancel that out. We can divide it out on both sides. The mass doesn't need to be there. We can factor it on the left side and then just divide it out altogether. So my equation now looks like this: 1/2 my initial velocity squared multiplied by my gravitational field times the initial height equals 1/2 my final velocity squared. I don't know h, so I'm just going to manipulate the equation. So I'm going to bring that initial 1/2 my initial velocity squared to the right-hand side by subtraction, and then just divide both sides by g. If I move the 1/2, since I have a 1/2 there and a 1/2 there, I can factor that out and just bring that down below. So I end up just having to multiply by 2, multiply by g. And then it's just a matter of plugging in the numbers, which you guys are experts at this point. Plug in the numbers. 11.7 is probably somewhere just a little under 140 minus 4 squared, so about 16. So you're probably somewhere around 120-ish. Divided by 2 times 9.81 meters per second squared, 19.62, if you will, meters per second square. So you have roughly 120 divided by almost 20. So it doesn't surprise me that you'd end up with somewhere around 6 meters in the air. And that's where the bird was when it passed on. So questions like this aren't uncommon, where you have to combine your gravitational potential energy with kinetic energy. You might see questions where it's like, hey, you have a mass of 5 kilograms and it's 20 meters up in the air. How much energy does it have? It's just it won't tell you that you have to use G. It's just something you'll kind of need to remember, that your acceleration and gravity is inherent in a lot of these problems. So I'm going to stop there and try to keep this video short. Try some of those problems, and of course email me if you have questions. So we will stop there.